This is your presenter Asloob Mudassar, and I am presenting slide number 120 of the course on laser physics. Question is, describe a practically demonstrated folded optical unidirectional ring resonator for producing single mode continuous wave laser operation, and which also provides an automatic control over the transverse mode operation. The answer is, consider an optical system, a folded ring cavity resonator shown in figure number 1 for continuous wave single longitudinal laser mode operation. The dye solution in the dye cell flows in the form of a liquid jet which acts as an active medium. The flow direction is kept perpendicular to the direction of the pump beam. So let me show you the figure first. This is the figure 1, schematic diagram of an optical system for single mode laser operation in a unidirectional folded ring resonator. So you can see the essential components of this. This is a pump beam, which is an ion laser beam acting as a pump beam incident on M0 concave mirror, and the light is focused on a dye cell perpendicularly to the direction of a flow of the liquid through the dye cell in the form of a jet. This is forming a beam waist. The beam waist is formed at the dye cell due to the mirror 1, because the mirror 1 will focus the light at the dye cell, and the light after being focused is diverged out towards the mirror M2. The mirror M2 will focus the beam such that the beam becomes incident on the mirror M3, forming a beam waist in between a location located between mirror 2 and mirror 3. And the beam waist is located such that the light after reflection from the mirror 3 becomes parallel, that is in the form of a parallel beam or the collimated beam. This collimated beam passes through the unidirectional device consisting of a Faraday rotator and a birefringent plate sandwiched between two plane polarizers with identical axes. Then from the unidirectional device, which selects a single longitudinal mode, the beam passes through thin atolon and then thick atolon, and then a birefringent filter, and then of course the beam falls onto an output beam, output coupler. Part of the beam is transmitted as an output beam from mirror M4, which is an output coupler, and the part is reflected towards the mirror M1. There is a parallel surface glass plate between the M4 and M3. This glass plate can be located at anywhere provided the beam is collimated. For example, it can be placed anywhere in the arm from mirror M3 to M4, or from mirror M4 to M1, anywhere between the places between the arm, anywhere. So the beam which is collimated from M4 is incident on M1, and M1 is again and M1 again focuses the beam, forming a beam waist at the location of the dye cell, and then this one pass is completed. So I am going to describe it. The whole lecture will be devoted for the discussion of this only one schematic diagram which I am showing you. So let me read again. Consider an optical system, a folded ring cavity shown in figure number 1 for continuous wave single longitudinal laser mode operation. The dye solution in the dye solution in the dye cell flows in the form of a liquid jet, which acts as an active medium. So you see that the dye is acting as an active medium. The flow direction is kept perpendicular to the direction of the pump beam. In a commercial unit, the pump beam is an ion laser beam, which is focused in the center of the dye cell. The focused pump beam sets the transverse gain distribution of the oscillating laser beam through the dye cell to lace in a single transverse mode operation. The folded ring configuration consists of 3 concave mirrors and an output coupler, a partially reflecting plane mirror. So let me show you the 3 concave mirrors. One concave mirror is M1, the other concave mirror is M2, the third concave mirror is M3. So the folded ring cavity laser ring resonator is formed by the mirrors M1, M2, M3 and M4, where M4 is a plane mirror, which is a partially reflecting mirror acting as an output coupler. So the folded ring resonator forms from M1 to M2, then M2 to M3, then M3 to M4, and then back from M4 to M1. So this is our folded ring resonator. Whereas the upper part is the part from the pump beam. That is the pump ion laser beam coming from in this direction from the ion laser source, and then of course it is incident on the concave mirror, which focuses concave mirror M0, which focuses the beam onto the dye cell, and this focusing is in the direction perpendicular to the direction of flow of dye through the dye cell. So you see that through the dye cell to lace in a single transfer mode operation. The folded ring configuration consists of 3 concave mirrors and an output coupler, a partially reflecting plane mirror, which was M4 mirror I have just shown you. The laser beam within the ring configuration is focused by the mirror M1 at the center of the dye forming beam waste 1. So you see that the mirror M1 is actually focusing the beam at the center of the dye cell and forms a beam waste 1 there. So this is the mirror M1. It receives the parallel beam, collimated beam from mirror M4, and then it focuses the collimated beam at the middle, at the center of the dye cell in the form of A, and forming a beam waste 1 there. And you can also notice the location of the beam waste 2 over here. This is the beam waste 2. So you see that when M1 focuses the beam diverges out towards the mirror M2. And the M2 again focuses the beam somewhere in the path between M2 and M3. So a beam waste 2 is formed as shown over here, and it is located in such a way by the mirror M2 that when the beam is incident from mirror 2 to the mirror 3 will make a collimated beam, that is the beam containing plane parallel wavefront towards the unidirectional device or towards the output mirror M4. So M4 will be acting as an output coupler. That is, it will give you an output beam also, and it will also reflect the beam towards the mirror M1. The mirror M2, now you see that I am going to explain the function of the folded ring resonator. The mirror M2 then directs the beam towards the mirror M3. The diverging beam towards the mirror M2 is focused on the path in the beam between M2 and M3, forming a second beam waist. The location of the second beam waist is adjusted such that the beam after reflection from M3 becomes collimated beam. So let's look back at this one. So this beam waist 2 is adjusted by the mirror M2 in such a way that when the beam is incident on the mirror M3, the beam becomes collimated. So this beams in the arm from M3 to M4 is a collimated beam, and also the beam in the arm from M4 to M1 is also a collimated beam. The collimated beam then travels through a unidirectional device and other components and then reaches the mirror M4, which is a partly reflecting and partly transmitting mirror. The reflected collimated beam from the mirror M3 is the reflected collimated beam from the mirror M4 is directed towards M1, and the cycle of the oscillation is completed. So you see that we started our discussion with the mirror M1, that the mirror M1 focuses the beam at the center of the dicell, and the diverging beam then incident on the mirror M2. The mirror M2 focuses the beam such that the beam is incident after the beam waist 2. It is incident on the mirror M3 in such a way that the mirror M3 generates a collimated beam towards mirror M4. The mirror M4 then reflect a part of the beam towards the mirror M1. So you see that this will complete one pass of the beam through this folded ring resonator. The reflected collimated beam is then directed towards M1 from mirror M4, and the cycle of oscillation is completed. A plain parallel glass plate mounted on a precision tilt mechanism is placed in either of the collimated path and is used to precisely control the optical path length of the laser of the ring cavity. So let me show you this parallel glass plate. You can notice that this is the parallel glass plate that has been placed in the path of a collimated beam lying between the mirror M4 and mirror M1. So this collimated beam, this parallel glass plate is mounted on a precision tilting mechanism, or on a precision rotating mechanism, so that this can be rotated slightly. In the figure, it is shown that it is lying perpendicular to the direction of a propagation of the collimated beam through the glass plate. But you see that this glass plate is mounted in such a way that it can precisely be rotated. So this way you can change the path length difference of the cavity. So when the path length difference of the cavity is generated, it means that you set the length of the cavity very precisely. In this way, you would be able to select different longitudinal modes. So you see that if many longitudinal modes are propagating, you have the possibility that you can tune your system or your this cavity only on one of the modes. So this parallel glass plate will provide you a means of selecting or a means of tuning different longitudinal modes. So this sentence is about the same glass plate. This provides a means of tuning the desired longitudinal mode and to bring it under the transmission profile of the etalon. So you see that we have placed two etalons, thin etalons and thick etalons, and they have their transmission profiles. Their transmission profiles have been discussed in slide number 119. So if you want to know the functions of thin etalon and thin etalon, I would suggest you consult previous two slides, that is slide number 118 and slide number 119. So you see that by tilting precisely or by slightly rotating this parallel glass plate, you actually change the length of the cavity. And by changing the length of the cavity, you provide a means that you can select different longitudinal modes. So tuning. This provides you a tuning for the longitudinal modes. And it also provides you the possibility that you can tune longitudinal modes in such a way that they fall in the transmission curve of the echelons. A unidirectional device, a Faraday rotator plus a birefringent plate sandwiched between two identical linear polarizers, and these two polarizers, which I have not shown, are actually sandwiching two main components. One is the Faraday rotator and the other is the birefringent plate. These two components have been sandwiched between two linear identical polarizers having identical axes. So this unidirectional device actually consists of four components: Faraday rotator, birefringent plate, and these two components are sandwiched between two identical linear polarizers having identical axes. And this unidirectional device has been explained in much greater detail in slide number 119. And you see that the components within this unidirectional device have not been shown. The collimated beam then travels through a unidirectional device. So the beam, that collimated beam I am talking about, is the beam reflected by the mirror M3. So this beam, which is traveling from mirror M3 towards the mirror M4, is a collimated beam. So this collimated beam will pass through the unidirectional device. So this is the unidirectional device in the sense that it will not allow the light to propagate. In the present case, it will allow the light to travel from left to right, and it will stop the light when it is traveling from right to left. That is why it is called a unidirectional device. The collimated beam then travels from a unidirectional device and other components and then reaches the mirror M4. So I should start from here. A unidirectional device, a Faraday rotator plus a birefringent plate sandwiched between two identical linear polarizers ensures the single longitudinal mode operation. The two polarizers, which form an important part of a unidirectional device, have been omitted from the setup, as the other optical elements have been placed with their surfaces inclined at Brewster's angle and maintain necessary polarization state within the ring resonator. So you see that the two polarizers, which are an essential part of a unidirectional device, are there, which have not been shown. That is, in the unidirectional device, I have not shown the Faraday rotator, the birefringent plate, and the other two linearly polarized linear two polarizers. These have not been shown. And the other components can be placed at Brewster angle in order to ensure the polarization state of the laser beam in the arm in the path from the mirror M3 to M4. So if you want to ensure the polarization state to remain the same between this arm, that is between the arm constructed by M3 and M4, the other components can be placed at the Brewster angles in order to maintain the state of a polarization in this arm. So let me read this last paragraph, last sentence. The two polarizers which form an important part of a unidirectional device have been omitted from the setup, as the other optical components have been placed with their surfaces inclined at Brewster's angle and maintain necessary polarization state within the ring resonator. The unidirectional device also ensures one-way propagation of the lasing beam. Laser tuning mechanisms are controlled by the combination of two Fabry-Perot and a birefringent filter. So you see that here the tuning mechanism is again stated over here in terms of the Fabry-Perot and the birefringent filter. The tuning mechanism is controlled by the combination of two Fabry-Perot and a birefringent filter. So you see that in the previous slide, that is in the slide number 119, I have discussed there an equation of the birefringent filter, which relates the wavelength of the light passing through the birefringent filter and also in terms of the width of that plate and also the phase produced by this filter, because birefringent filter will produce two beams, ordinary beam and the extraordinary beam, and a phase difference between these two beams can be produced at will by rotation of the birefringent filter. So when you rotate the birefringent filter, you in principle actually control the phase difference between the two emerging beam from the birefringent filter acting as a ordinary beam and an extraordinary beam, and when these two beams combine, when they exit the birefringent filter with some predetermined phase difference, then of course the polarization state, the linearly polarized form is light is generated by the combination of the two beams, that is the ordinary beam and the extraordinary beam, when they exit the birefringent filter. So when they exit, the two beams combine with a predetermined phase difference, and so the polarization state of the light is rotated. The two etalons, a thin etalon and a thick etalon, normally have different spectral ranges or finishes. The thick etalon discriminates between two adjacent longitudinal modes. That is, the two adjacent longitudinal modes are identified by the thick etalon, and the thick etalon will allow the two consecutive longitudinal modes to pass through the system. Because the transmission curve of the thick etalon is adjusted in such a way that two consecutive modes in the cavity can pass through this thick etalon, and the thinner etalon chooses the required transmission peak around the required longitudinal mode. So out of these two adjacent longitudinal modes which pass through the thick etalon, which are selected by the thick etalon, they propagate towards the thin etalon, and the transmission curve of the thin etalon is chosen in such a way that it selects only one of the two adjacent longitudinal modes. So in this way, a single longitudinal mode is selected for laser operation. So you see that I think that the things have been explained very well. So you see that the schemes over here, that is the unidirectional device, the thin etalon, the thick etalon, the birefringent plate, they actually serve the purpose of selecting a single longitudinal mode. And you know that this parallel surface glass plate will help you to tune the modes. For example, if the components between the arm M3 and M4 allow many longitudinal modes to propagate within the laser cavity, then of course this parallel glass plate will be able to tune one of such longitudinal modes by precisely tuning the length of the cavity. So you know that the propagation of the longitudinal modes within a laser cavity depends upon the length of the cavity. So if you precisely change the length of the cavity, it means that you can allow other longitudinal modes, you can select other longitudinal modes to propagate within the laser cavity. So this glass plate serves the purpose of tuning or selecting one of the longitudinal modes to set up in the ring laser cavity. And then unidirectional device, thin etalon, thick etalon, birefringent filter, etc. These provides you a means of choosing at least one longitudinal modes, and then of course the output beam will be a laser beam with only one longitudinal modes. So you have one longitudinal mode at the output, and at the same time you have a much longer laser cavity in the form of a folded ring resonator. So due to much larger size of the laser resonator, a very strong laser output beam can be produced within the laser cavity, and of course a part of that can be taken as an output beam. So a much longer, so much powerful beam can be generated using a setup shown over here with a single, with a precisely single longitudinal mode. So I think that the explanation given is adequate. But I would suggest to you that if you want to have a detailed discussion, if you want to understand for example, the function of the unidirectional device and the functions of the etalons and the function of the birefringent material, I would suggest to you to have a look at the last two slides, that is the slide number 118 and the slide number 119. So this is the end of slide number 120.